Greetings, mathophiles. Welcome to the first in a series of 3 videos on the core calculus concept of the definite integral. In this first one, we'll take a look at the major building block for the definite integral, which is the Riemann sum, and we'll talk about how that arises out of our motivation to solve what I have elsewhere called the area problem. In the second video, we'll give a formal definition of the definite integral, and we'll work some examples. And in the third video, we'll take a look at the various properties that apply to definite integrals. You'll see on your screen a Desmos page in which I've highlighted a region that we're going to be working with, and that is the region bounded by the x-axis, the graph of the function f of x equals x plus x squared, the vertical line x equals 2, and the vertical line x equals 5. And the way we tend to refer to this is the area under the graph of f on the closed interval 2, 5. So the way we're going to approach this is as follows. We are going to divide this interval from 2 to 5 into a number of subintervals, and that number of subintervals can certainly vary. I believe I'll start with 3 because that gives us a nice subinterval width of 1. And what we're going to do is as follows. We're going to identify on each subinterval some value of x. So that first subinterval runs from 2 to 3, and we can take any x on the closed interval 2 to 3 and plug it into the function and get a value. And in the picture you see here, the value we've plugged in on that first subinterval is x equals 2. So you plug in 2, you get a value out. And we take that value to be the height of a rectangle on that subinterval. And then we do it again for the subinterval from 3 to 4. And we've again taken the leftmost value, the least value on the subinterval. So we plug a 3 into the function, we get some function value, and that becomes the height of the second rectangle. And finally, we do this for the third rectangle. In principle, you could choose any x you liked on any of the subintervals according to any rule you wanted or according to no rule at all. In practice, life stays sane if we have the same rule for all of the subintervals in a given situation. And almost always, that rule is grab the value at the left edge, grab the value dead in the middle, grab the value at the right edge. So left endpoints, midpoints, and right endpoints. It does make a difference in a given situation. If I switch from left endpoints to midpoints and from midpoints to right endpoints, we certainly see that if the function is not constant on the subinterval, that choice is going to affect the heights of the rectangles, which is going to affect our estimate. So that's a thing to be aware of. Also, though, it's pretty clear that these are, in this situation, lousy estimates. There is a lot of area under the rectangle, these 3 rectangles, that is not under the graph of the function, and this does not seem, at first glance, to be very promising. But there is a thing you can do that we're going to keep referring back to, and that is that you can keep increasing the number of subintervals, and as you do that, you tend to get a better and better look. So here's the right endpoints with 26 subintervals rather than just 3. Here are the midpoints. Here are the left endpoints. And at least visually, as far as we can tell, we seem to be doing a better job. Now, you probably already know enough calculus if you're watching this video to sort of see where this is headed. But we're not going to take it all the way there until the second video. Our next task is to take a look at the conventional labeling schemes for this work and some of the terminology as well. So we're going to imagine that we have a continuous function f on closed AB, and we're going to take that interval from A to B, and we're going to divide it into n subintervals of equal width. In principle, the widths don't have to be equal. Life is much nicer if they are. And we're just going to label the boundaries between these subintervals with subscripted x's. So I'm going to let x sub 0 or x naught be another name for A. And then we'll have x1 and x2 and so on. B would then be x sub n. The boundary here between these last two subintervals, that would occur at x sub n minus 1. And we have a bunch of these rectangles in between. And here we have the generic kth rectangle. So k will be the index we'll use to count which rectangle we're on. And so how should we label that? Well, we have x1 at the right edge of the first rectangle. We have x sub 2 at the right edge of the second rectangle. We have x sub n at the right edge of the nth rectangle. It seems logical that we would have x sub k at the right endpoint of the kth rectangle, and so x sub k minus 1 would be the next one to its left. So let's take that kth rectangle and blow it way up. And that's what you see over here at the right. So this is x sub k. This is x sub k minus 1. The width of this one, and indeed the width of all of them, we can call delta x, and that will be the total width, b minus a, divided by the number of subintervals, which is n. What are the heights? Well, we're getting the heights by choosing some x on the subinterval, plugging it into the function, and having that value define the height of the rectangle. And then the rectangle area is our estimate for the area under the curve on the subinterval. I feel like I want to call it x sub k, but that's already in use. And there are actually a bunch of x's on the kth subinterval. So what I'll do is I'll show that it's all special by giving it a superscript star. So of all the x's we could have chosen on the subinterval, we're choosing this one. It's special, it gets a star. And then this height is f of x sub k star. So these were the widths. The heights then of all of these rectangles are f of x sub k star for the kth rectangle. Their areas are their heights times their widths. So f of x sub k star delta x. And my estimate of the entire area under f, all the way from x equals a to x equals b, is then going to be the sum of all these rectangle areas from the first one to the nth one. This thing is a big deal. It's called a Riemann sum, after Bernard Riemann, who is credited with having worked all this out. And so this is kind of the labeling scheme and the nomenclature that we're going to use as we build up the definition, and that you in all likelihood will return to when you look in earnest at the question of how to get good approximations using technology. Now let's take a look at some labeling that is specific to how you choose the x sub k stars. If you choose the x sub k stars to be right endpoints, then we can actually come up with an expression that would give the x sub k stars. Because how do I get to the right edge of the kth subinterval? I start at A, and I go the right number of delta x's. And to get to the right edge of the kth subinterval, the right number of delta x's to go is k. So I can say that x sub k star, when I'm using right endpoints, is a plus k delta x. I can then write the sum as f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x, and so on up to f of x sub n times delta x. I can then factor out the delta x and call it b minus a over n, and I'm left with f of x1 plus f of x2 plus f of x3 and so on up to f of x sub n, and you'll see that formula on your screen. I could take those f's and just call them y's. So I could take f of x1, call it y1, I could take f of x2 and call it y2, and so on, and that gives me a slightly more streamlined formula. So if you needed an expression that would pop out the right endpoint sum, this would be it. It's b minus a all over n times the sum of all of the function values except the one at the very leftmost, f of x naught. If you were at the left endpoint, things don't change all that much, but your x sub k stars are going to be 1 delta x less than they were at the right endpoint. And so your x sub k stars are going to be a plus quantity k minus 1 times delta x. Your sum then is going to be b minus a all over n times f of x naught plus f of x1 plus f of x2 and so on up to f of x sub n minus 1. So when you compare the left and the right endpoints, all of these function values at these breakpoints between subintervals sort of do double duty, except the very leftmost one, which is not anybody's right endpoint, and the very rightmost one, which is not anybody's left endpoint. And in the left endpoint case, very similarly to the right endpoint case, you can rewrite that a little bit more nicely, as you can see. Finally, the midpoints are a little bit trickier notationally. They are a halfway between k minus 1 delta x's and k delta x's to the right of a. So they are a plus quantity k minus a half delta x. And in situations where you actually have to do some algebraic wrangling, that 1/2 is a bit of an annoyance, but what are you going to do? So you can then factor out of your sum, again, the delta x, so that's the b minus a over n. And then you have to, unfortunately, get a little more in depth with your notation here as well, because the midpoint of the first subinterval is halfway between x naught and x1. So it is f naught, x naught plus x1 all over 2, and so on. So we have to take the value of the function at those locations, add them all up. You can nicen up the notation a little bit if you label those as y sub first midpoint and y sub second midpoint and so on. It's not nearly as prescriptive in terms of how the values are to be arrived at, but it's certainly much more congenial to write down. We are back on Desmos looking at our original function, which was f of x equals x plus x squared on close 2(5). And I want to explore a little bit the question of what happens when your n's get bigger, and we're going to then flesh that out more formally in the next video. So we have here the left endpoints, and I've stuck down here on the left the area sum, what we now can call the Riemann sum for n equals 3 and left endpoints for this function on this interval. And I'm going to go ahead and start increasing the number of subintervals. And as you can see, this number is climbing. It's now in the neighborhood of 49 or so, and here comes the slider on its way to 100. So if I increase my number of subintervals using left endpoints to 100, as you can see visually, there seems to be much less difference between the Riemann sum area and the area under the function itself. So remember that number 49, and we're going to go back to a small number of rectangles, and we're going to look at the right sum. So here is the right Riemann sum. That's about 62. And I'm going to go ahead and do what we just did a moment ago, which is to increase the number of subintervals, but this time using right endpoints. And as you can see, this works its way down to something in the neighborhood of about 50 or so. And of course, the midpoint estimate would have to lie in between because this function is increasing on this subinterval, right? So as the n gets bigger, all three of these Riemann sums, which we're using as approximations to the area under the curve, all three of these Riemann sums are converging toward one another in value. I'll place a little table on the screen, and you can see how nicely this convergence occurs as we work our way up from a smallish number of rectangles up to 100. And this, I think, will suggest to many of you that the way we're going to ultimately proceed would be to take the limit of this Riemann sum as the number of rectangles got larger and larger without bound. And if that is your surmise, I think you're going to be able to see some confirmation in the second video. Until then, happy mathing.